Greetings and welcome to the introduction to astronomy. In this lecture, we are going to talk about ancient astronomy going back to ancient times and up through the Dark Ages. And we will pick up later on with the Renaissance and move into modern times. So this is our beginning of the study of very early astronomy. So let's go ahead and get started. And one of the things we can look at what was the sky? The sky was very important to early people. And why? Well, it was a calendar because we did not have modern technology. So how did we tell when the seasons were beginning and ending? And it was very difficult to tell them exactly. As you know, it's not always warm all the time, going right up to, say, summer. You do get some colder days. So how do you tell exactly where that was? So, for example, the ancient Egyptians used the rising of Sirius, what they call the heliacal rising of Sirius, when it was first visible in the morning sky when it first appeared, because that occurred about the same time that the Nile would flood, bringing water to the desert areas of Egypt. So it was important to know when that flooding was coming to be able to be prepared. Navigation was another important thing where this was used. And that was used by the Polynesians in order to navigate. How do you navigate at sea without modern technology? Well, even just hundreds of couple hundred years ago or less, we did not have a lot of technology to be able to navigate the oceans. So we could use some things to travel across the Atlantic. Certainly, if you head west from Europe, you would end up in one of the Americas. But where on it would you land and how would you know that? And the Polynesians were very good at being able to navigate between the islands of the Pacific, where you have no landmarks around, but would still be able to get from one point to another successfully and do that using the stars. So the patterns of the stars and their positioning in the sky was important for a calendar and for the use in navigation. Now, very early monuments, and we're only going to look at one here, although there's lots of them scattered all over the world. Stonehenge is one of these, and it is a collection of very massive stones that are on the plains of Salisbury in England. And you can see them here, massive stones put together and other stones put on top of them. And it's quite possible that this was used as a calendar. And we see alignments with various things here. And if we look at Stonehenge towards the center, when we look out towards this direction, that is aligned with the sunrise on the first day of summer. And only on that day, the sun will rise in a very specific location over what is called the heel stone out there. Now, there are other alignments that perhaps work as well. But one of the problems with these early monuments is that we do not have instructions. So there's no instruction manual. We're set trying to decipher by the alignments that we see, not knowing whether all of them were necessarily done intentionally. Now, as I said, there are many other monuments like this around Europe, around the Americas, Africa, Australia, all over the world, where these kind of alignments, not specifically like Stonehenge, but where we see monuments, pyramids built to line up with various astronomical events. Now let's move forward a little bit into the early Greek astronomy. This is kind of the beginnings of our understanding of the universe. And there's several astronomers here that I'm going to mention, and we'll look at a few of these in more detail. Eudoxus gave us one of the very early models of the universe. Aristotle gave us a couple of big things. One, explaining that the Earth is round, that the Earth is a sphere, and that the universe is geocentric. Now we now know that this is not the case. So he was right on the Earth being round, but wrong on a geocentric universe. Eratosthenes was able to measure the circumference of the Earth. So following on the Earth being round, you could measure the circumference or how far it is around that. Aristarchus was one who gave us the idea that the sun and not Earth was the center of the universe. Now, this was not accepted at the time. And the fact that so many writings do not exist from this, we don't have the direct writings of Aristarchus to be able to see exactly what his thoughts were on this. But it was put forward that perhaps not Earth is not the sun, a center of the universe. The Earth is not. Uh, the center of the universe, but the sun is instead. We'll look in more detail at Hipparchus, who gave us stellar magnitudes, how to measure the brightness of stars, and measured precession. And then we'll end up with Ptolemy here, who gave us a mathematical model in his book, The Almagest, that really was a way to be able to calculate positions in the sky. So let's look at a few of these in more detail, starting with Aristotle, who started out with the fact that the heavens were perfect. So what was in the heavens must be perfect. What is on earth is imperfect. And that means that everything moved in circles and at a uniform speed, not speeding up or slowing down. And this really gave us our foundation of planetary motion for over 1,000 years, based on the ideas of Aristotle. Now, based on that, we can learn a few more things and we can start to be able to piece together the orbits. But if you remember, Aristotle also told us that the Earth is a sphere. And once we know it's a sphere, we can measure how big it is. And that was Eratosthenes here measuring the circumference of Earth. Now, here is a diagram showing that there is a well at Syene, shown here, where the sun would shine straight down on the first day of summer. And that meant that it was directly overhead. However, an object at Alexandria cast a shadow. So the sun was not quite directly overhead. It still cast a small shadow, in fact, about 7 degrees. Now he could use that. The fact that this angle is 7 degrees also meant that the angle here at the center of Earth was 7 degrees. So if he knew 7 degrees as a ratio, 7 degrees to 360 degrees, because 360 would be a full circle, that is equal to the distance between those two cities divided by the circumference of the Earth. Well, if we measure the distance between the cities, we can then calculate the circumference and how big the Earth was. Now, there are questions as to how accurate he was, but certainly the knowledge that the Earth was spherical was very prominent in these early times with the early Greek astronomers. And they knew for sure that Earth was a sphere and did go about measuring its circumference. Now, another astronomer, Hipparchus, gave us the idea of magnitudes. Now we'll come back to magnitudes in a later chapter, but essentially he divided stars into categories based on their apparent brightness. The brightest stars were those of the first magnitude, and the faintest stars that could be seen were those of the sixth magnitude. So that was the range, and it kind of gave us a backwards magnitude system, because star of magnitude 1 is now brighter than a star of magnitude 6. So we still use this system, and it's based on the original work of Hipparchus, but it is backwards. So a smaller number means a brighter star, a larger number a fainter star. He also determined precession. Precession occurs because the Earth spins like the top pictured here. So the Earth spins very quickly on its axis once per day. And it also makes a slow rotation around the sky, taking 26,000 years. And that causes things like the pole star to change over time. So what we see as the pole star now is Polaris. However, 13,000 years from now, the pole will be much closer to the bright star Vega. After that, the star Thuban. And in between, there will be times when there is no pole star. And 26,000 years from now, we will be back again to Polaris being the pole star. So it's a regular cycle, but takes 26,000 years and is constantly changing the position of the pole, which changes the coordinate system that astronomers use. Now, Ptolemy with the geocentric universe giving us the idea, we had the idea that the universe was geocentric or earth centered. So geo meaning earth, and the earth was at the center of the universe. Now, in order to make the orbits work, that required quite a complicated system. So what you really needed was, here was the center, and the earth was actually offset a little bit from that. And on the other side of the center was an equant point. The equant is the point opposite that central object, Earth, and is the point around which the other object appears to revolve. So the object doesn't revolve directly around Earth, but around this equant point. Now what we see is that as this moves around, then the path is the deferent, that's the orbit here. But the planet itself actually orbits on an epicycle. So there's a central point here with nothing at it, where this point goes around on the epicycle, while this piece goes around the rest of the deferent. So what it makes is, as we talked about in a previous lecture, it allows to explain retrograde motion. And it can allow changes in brightness of a planet as well, because sometimes it's closer to Earth and sometimes it's further away. And by adjusting the positioning, the size of the epicycle, the size of the deferent, to very good accuracy for the time, we were able to map out exactly how big the solar system was, and be able to calculate the positions and predict the positions of planets in the future. Now this ends our story kind of, but we've got one more little bit to look at here, because with the fall of Rome in the early part of the millennium, then there was a decline in Western science. And as the West descended into the Dark Ages, there was very little advancement in the West. However, things did not stop. The Indian and Arab astronomers continued the work. They took and developed, translated the works from Greek, and they developed new mathematics. Now the Greeks did everything based on geometry. The Greeks were big at geometry and using that for the orbits, but they did not have the concept of algebra, and that was developed by the Arab astronomers who continued that. We gave some of these early ones. An early Indian astronomer, Aryabhata, actually gave us the idea that the Earth rotates as a better way to be able to explain the motions that we see. Why? Because that does not require then the whole celestial sphere to rotate around Earth. It's a lot easier to have the Earth rotate. We also have Ulugh Beg, a Muslim astronomer, who built one of the largest observatories of the time, probably the largest observatory of the time, and continued observations. Then this work then returned to Europe during the Renaissance. So during the Renaissance, books were returned to Europe. Europe would collect books from other that had been translated, and additions made to them and corrections made to them, and brought that back, leading to a developments of the new model of the solar system that we will see in a couple of lectures. So things did not stop after the fall of Rome. They actually just continued on in other parts of the world, and then came back to Europe, and further advancements continued throughout that time. So let's go ahead and finish up this section with our summary. And what we look at, again, the study of the sky was important for two reasons: the calendar, keeping time, and navigation. We looked at Stonehenge as an example, but there are many other ancient monuments that we can look at as well that may have been used for timekeeping early on. And we looked at the Greek astronomers who gave us a geocentric model of the universe that lasted for 1,000 years. And then that work was improved upon by the Indian and Arab astronomers during the Middle Ages. And then Europe will pick up with that again and take those modifications and continue to build on them in the Renaissance that we will discuss later. So that concludes this lecture on ancient astronomy. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone,